Alright guys, so today's lesson we're going to kind of press pause for a second and introduce you to what are called organic structural conventions. And so far this week we've been working with molecules that are pretty small and relatively simple, things like CH4 or CO2. And as we've been working with those smaller molecules, we've been reviewing some concepts like geometry and talking about some new concepts as hybridization. And we tried to introduce those while the molecules were still relatively simple. However, as we begin to move forward in the course, the molecules are going to get larger and more complex. And while it isn't too much trouble to kind of sketch out a carbon dioxide molecule right quick, it would be a lot of trouble to sketch out by hand a caffeine molecule or a drug molecule. And so we're going to need to develop some different conventions or symbols for representing larger, more complex molecules in a more convenient, kind of fast way. And so we're going to introduce kind of 4 different conventions that we can use on the symbolic level to represent organic molecules. We've got the molecular formula, the expanded structural formula, condensed structural formula, and then kind of what organic chemistry is known for is the skeleton or keculae formulas. And so what I'm going to do is kind of go over a couple of examples that aren't on your chart. Then I'll talk you through the first 2 rows of your chart, and then you'll be able to work the rest on your own. And so within your chart, you've kind of got the definition of each of these 4 structural conventions within organic chemistry. And so I'm going to start with a simple example that is propane. And I'm going to begin by giving you the expanded structural formula. So propane has 3 carbons, and each of those carbons has enough hydrogens attached to make the carbon have 4 bonds total. So each of the carbons is bonded to 4 other atoms. All right. And so a couple of features to note about the expanded structural formula is that one of the benefits of this convention is it shows you exactly how the atoms are arranged by noting which atoms are bonded to which other atoms, all right? So it shows you what order the carbons come in, it shows you which hydrogens they're bonded to, how many hydrogens. However, one way in which this convention is lacking is it doesn't really reflect molecular geometry. You'll notice in this example and the others on your chart, the expanded structural formulas are typically drawn with straight bonds. So they're not really reflective of the overall molecular geometry of the molecule. If I showed you the molecular geometry, it would actually look kind of something like this. If you look on the right-hand side here, and we see that those bonds are not indeed all straight up and down. And so we'll get to kind of how to show that in a different convention here in a second. All right, let's go back now. So I'm going to start with that expanded structural formula and then teach you the other conventions from there. So let's go back to the left here and spend a little bit of time talking about the molecular formula. Now, the molecular formula is what provides the least amount of information about the molecule. That being, it only tells you how many of each type of atoms you have. And what we'll do is we'll typically list the atoms in order of carbon first, hydrogen second, then oxygen and other elements following. So here we have 3 carbons, so we're going to write the symbol for carbon and a subscript of 3 since there are 3 of them. Then for our hydrogens, we see that there are 1, 2, 3, 4, 5, 6, 7, 8 hydrogens total. So the molecular formula tells us the number of carbons and the number of hydrogens overall in the molecule. We don't happen to have any other atoms in this case. Now, where this molecular formula might come into play and being useful is when we're needing to determine molecular weight, or aka molar mass. We can easily add up the mass of 3 carbons and sum that together with the mass of 8 hydrogens. So that's where the molecular formula is really helpful to us. Now, the condensed structural formula is kind of a combination of the molecular and the expanded structural formula. And what it does is it only lists element symbols and subscripts, but however, it groups them together so that you can kind of get a hint at the connectivity within the molecule. And so what we're going to do for the condensed structural formula is we're going to start at the left of the molecule and work our way to the right by breaking it up into pieces. So our first portion of the molecule here is kind of based off the center carbon. And what we see is we have one carbon and it's attached to 3 hydrogens. So that's kind of the first piece or group of the molecule, CH3. Now as we progress further along the molecule, we have this middle part here that consists of 1 carbon and 2 hydrogens. So our first group is CH3, the next group in line is CH2, and then we find ourselves back at another CH3 group to finish off the molecule. So our final portion of the condensed structural formula will be CH3. So we're just using symbols and subscripts, however, we're grouping those atoms together to kind of show how those pieces are connected within the molecule. Now finally, on to the fun one, in my opinion, the skeleton or keculae formulas. So where this comes into play is really related back to the definition of organic chemistry, being the study of carbon-containing molecules. And so organic molecules are going to have oftentimes a lot of carbon in them. And so what the skeleton or keculae formula does is it replaces carbon atoms with lines, all right? And so what we're going to find, we'll kind of look at these examples here right quick, is that every time you come to a point on a line, it's going to represent a carbon. So this end point on this line represents a carbon, and also this bend where those 2 lines are connected represents a carbon as well. So the next molecule, here we have a carbon on the end of that point. We have a carbon here where the 2 lines connect directly, and a carbon here where we have another connection of lines. Now what you'll also notice is that the hydrogens tend to, quote, disappear. Now they really haven't gone anywhere. One thing that's unique about the keculae structure is we don't show those hydrogens connected to carbons or nitrogens, all right? Sometimes the nitrogens will show their hydrogens, but mainly the carbons, we kind of just assume or understand that the hydrogens are there, even though they're not drawn out specifically. Now the reason we can do that is because carbon is very consistent in making a 4-bond pattern. Carbon normally has 4 bonds. And so the way we can reason from this is if we focus on this carbon here, it's currently involved in 1 bond to this second carbon, that red dot. So what that means, if that carbon is only involved in 1 bond, it must have at least 3 other bonds present. And we're going to assume that those bonds are connected to hydrogens to complete that need for 4 bonds. And so that's how we kind of figure out how many hydrogens there are. Now, when we go to draw this for propane, we see that we have a total of 3 carbons in our molecule. So what I'm going to do is going to put my pen down at a point, and that's going to represent carbon 1. At the end of that line will be carbon 2, and then I'm going to bend downward for carbon 3. So this represents carbon 1, carbon 2, and carbon 3. Now you'll notice that keculae structures tend to look a little zigzaggy. And the way they're drawn in a zigzag, where you kind of alternate going up and going down with your line, is to represent some of the molecular geometry that you would see within the molecule. Now when you have lots of carbons, they tend to form tetrahedral shapes since they're bonded to hydrogens kind of in a 4-bond pattern. And so what we see is when we put that chain of the molecule together, we kind of have tetrahedrals going on each of the carbon, and that forms almost what looks like a kind of triangular zigzag shape. And if I added more carbons, that triangular zigzag would keep going. And so the Keculae structure does give us a little bit of a hint into what the molecular geometry of the molecule is like. All right, so there is our structure for propane. And again, we're not drawing in the hydrogens, but we know that they're there. Carbon 1 is bonded to one other carbon, so that means he would need 3 additional bonds to hydrogen. Carbon 2 is bonded twice already, so he only needs 2 additional carbons. And then finally, carbon 3 is only bonded one time, so we would understand that he has 3 additional bonds to hydrogen to get him to a total of 4 bonds. So let me erase this and draw this a little more neatly one more time. All right, now before we get into the examples on your chart, let me do one more example that actually came up in your reading in Napoleon's buttons for your intro to organic chemistry, and that was acetic acid. And so I'm going to start with the Keculae structure here, and we're going to go backwards and kind of fill in the other pieces. So here is the Keculae structure for acetic acid, and sometimes instead of the OH being together, you may see the H kind of drawn separately as a bond. So either one is fine, either left as OH or showing that the H is connected to the oxygen. All right, so now let's see if we can work our way backwards and fill in the missing pieces from the skeleton or Keculae formula. Okay, so what let's do first is let's kind of count and see how many of each element we have. So we know that each kind of point on a line represents a carbon. So far, for our molecular formula, it looks like we have 2 carbons. Now, what we have to do is figure out how many hydrogens we're going to have. This first carbon that I have highlighted is only bonded one time. So that means we kind of understand that there are 3 additional hydrogens there. The second carbon that's highlighted in blue is already bonded 4 times. It has a double bond plus 2 single bonds, so there are no additional hydrogens there. However, there is a 4th hydrogen connected to that last oxygen. So I have a total of 4 hydrogens in that molecule. Now, what I need to do is include the oxygens. So I have 1, 2 oxygens. So my molecular formula is going to be C2H4O2. Now let's see if we can write our expanded structural formula for the information we have. So I know that this end carbon, or end point on my line, is representing a carbon. So that will be a carbon, and we've already talked about how it's understood that there are 3 hydrogens attached. Now, let's move on to the second section of the molecule. Here I have a carbon that's double bonded to an oxygen and single bonded to another oxygen that's connected to a hydrogen. Now, when I'm drawing my expanded structural formula, it's a good idea to go ahead and put in the lone pairs. And you'll notice that a lot of times in Keculae structures, the lone pairs may be left out, even though they're there. And that's kind of the idea, is the Keculae structure is very simple. It's designed to be shorthand that you can pop out very quickly. But in your expanded structural formula, it's a good idea to go ahead and get in that habit of putting in those lone pairs to remind yourself that they're there. Because the presence of lone pairs is going to be a key kind of trigger for chemical reactions that we'll talk about later in the course. All right, so now finally for our condensed structural formula, let's take it one piece of the molecule at a time. So we've got our piece centering around our first carbon here. So that will be, whoops, change my pen, can't write with a highlighter. So our first piece is CH3. Then, why I chose this example is because this last portion of the molecule is actually going to be a piece all by itself. It's all connected to this carbon. And the way we're going to express that piece is COOH. It kind of looks like Q. And that is going to be characteristic to any time you have a carbon double bonded to one oxygen and single bonded to a second oxygen with an H. This portion of the molecule we'll later learn is referred to as a carboxylic acid. So anytime you see COOH, that's referring to that particular configuration. And I think you've got that in this second example that we'll go over here in a moment. That COOH, again, that's characteristic of a carboxylic acid portion. All right, so that's it for this kind of first example. I'm now going to walk you through the examples on the first 2 rows of examples on your chart, and then we'll get you on your way. All right, so let's kind of walk through these first 2 examples in your chart right quick, and then we'll let you be on your way. So we've got our 4 conventions: molecular formula, expanded structural formula, condensed structural formula, and the skeleton or Keculae formula. And so essentially what you'll do in your chart is whatever information they give you, you'll kind of use that to figure out whatever information is missing, and that's what you'll fill in. And I think on your chart, the first 2 rows are actually all filled in for you, but I figured it wouldn't hurt to walk through those together, and then we'll let you work on your own. All right, so we've got this first molecule here, C2H6O. So a total of 2 carbons, 6 hydrogens, and 1 oxygen, and the expanded structural formula kind of shows how they're arranged. So again, to do our condensed structural formula, we want to write the atoms in groups. So our first group is CH3. Then our second group, CH2. And then finally, we have an OH group at the end. So OH, that's known as a hydroxyl group. All right, so now for our skeleton or Keculae formula. So again, we're not showing the carbons or hydrogens. We use the lines for the carbons, and then the hydrogens are just understood or assumed to be there. So we've got carbon 1, carbon 2, and then that second carbon is going to be connected to an oxygen, which is also connected to a hydrogen. Now you can either leave the oxygen and hydrogen written together, or it's also okay if you would like to show the hydrogen connected out to the side. But we're not going to show the hydrogens that are connected to these carbons represented by our lines here. So you've got 2 carbons. This leftmost carbon would be understood to have 3 hydrogens attached, and then this middle carbon would be understood to have 2 additional hydrogens attached. So that would be your Keculae or skeleton formula. Now let's go ahead and move down to the bottom formula, where the only thing that I've been given here on mine is the skeleton or Keculae formula. And so we can just work our way from left to right if y'all want to, and start out with the molecular formula. Now again, we're going to have to do a little bit of reasoning here to figure out how many carbons we have. So remember, every kind of end of a line or kind of bend in a line is going to represent a carbon. So it looks like we have 3 carbons total. So we've got C3. Then next, we need to go ahead and count our hydrogens. So every carbon that we just marked, we need to check and see if there are any hydrogens attached. This first carbon is only involved in 1 bond, so that means that there should be 3 hydrogens attached to it. So we're going to have 3 hydrogens for this first carbon. Now, this nitrogen, it also is kind of missing a bond. It only has 2 bonds at the moment and 1 lone pair. And nitrogen, if we think back to our patterns, is often involved in 3 bonds. And so this nitrogen is also possessing kind of that hidden 1 hydrogen as well. So there's technically another hydrogen bonded to that nitrogen to give it its normal 3 bonds. All right, so that goes with that nitrogen. Then if we look at this carbon here, it's only involved in 2 bonds, which means it has 2 more hydrogens. Then this carbon that's attached to the oxygen, it's already involved in 4 bonds. It has a double bond and then 2 single bonds, so there are no additional hydrogens. But we do have a hydrogen attached to this final oxygen. So if we add that up, 3 plus 1 plus 2 plus 1, that's going to give us a total of 6 hydrogens. So we've got C3H6, And sorry, my writing isn't the best. I've kind of got my computer tilted at a funny angle here so I can use a different mic to make the audio better. But anywho, we'll just carry on. And then if we look at our nitrogen and oxygen, we have 2 oxygens and 1 nitrogen left. And so you can either do NO2 or we can write that as O2N as long as we get those in the formula. Okay. So now let's see if we can tackle our expanded structural formula. So we're going to start from left to right, and then we're going to start with this carbon that we've already said has 3 hydrogens attached. So let's get those 3 hydrogens in there. Then we come to our nitrogen, which has a lone pair, but we said it also has kind of 1 hydrogen that's understood to be attached. Then the next piece we come to is another carbon that we said has 2 attached hydrogens. And then finally we come to our 3rd carbon that's attached to an oxygen by a double bond, another oxygen by a single bond, and then finally that single bonded oxygen is attached to another hydrogen as well. And it's good habit when you're doing your expanded structural formula to get in the practice of drawing in your lone pairs. You'll notice that your lone pairs, especially on oxygens, aren't always drawn into the Keculae structure, but that doesn't mean they're not there. So when you're doing your expanded structural formula, if you get in the habit of putting in those lone pairs, it will help remind you that, hey, those really are present on the oxygen, and those will come into play in a lot of the reactions that we go over later. All right, let's finish this guy up. Condensed structural formula. So again, start from the left, where we start with a CH3 group, then we have an NH piece, then a CH2 piece, and then we end up with one of those carboxylic acid pieces that's COOH. Again, that's characteristic of this double bond to an oxygen and then single bond to an oxygen bonded to a hydrogen. All right, so what your task will be is to kind of finish the rest of the chart front and back. You're welcome to print off the chart and write directly on it if you have access to a printer. If not, you can use kind of an electronic notation software online to write on it, or you can easily just kind of grab a spare sheet of paper and kind of make your own chart as you go along. And then you'll take a really nice picture for me and upload that to Schoology so I can take a look at your work. And I don't want you to be discouraged. I don't expect everything to be perfect, this first time through. You're just learning. But what I would like to see is a good try, and for you to ask questions if you have them. So don't be discouraged if you're not completely sure on your answers, but just get in there and give it a good try, and these skeleton formulas will come to you with more time. Now, if you're having to submit kind of pictures of your assignments for either this class or another class, an app that I highly recommend is called Cam Scanner. If you have an Android or iPhone, it will work on either of those. But what it is it kind of turns your phone into a PDF or photo scanner, and it creates really nice, clear, and clean images that you can submit. I used this a ton during college. I still use it today. So highly recommend if you want to kind of up your picture submission game to Schoology. But anyways, I think that is all for today. Just let me know if you have any questions or if I can help you in any way. And if not, I'll see you next time, and have a great rest of your day.